All right, hi everyone. Welcome to the last week of class. It has been very fast-paced, I know, you and me both. So I just want to take a few moments to go through some of the most commonly asked questions regarding homework number 3, which is due today, and take a moment to just discuss some of the big picture topics that are in that lab. So if you have any questions, you can go ahead and send those through to the chat and I'll answer them. But real quick, the first one is about rate of change. Okay, and we're using real data. Okay, so one of the fun things that happens with real data sets is you might not always have data for the exact time periods you're looking for, which is what happens in the ice core data, right? We only have samples at every discrete sampling point. So for example, when I say find the change or the rate of change in atmospheric CO2 over 25,000 years, you have to find the sample that is close in age to 25,000 years. There's not an exact 25,000 year sample, but there is one that is very close in age to 25,000 years ago. In terms of rate of change, when we think about how much an object or a variable changes, we're really thinking about basically the slope of that variable. So the rise over run. And so with CO2, I'm asking you to tell me how much CO2 has changed over some time period and the rate at which it's changing. So you would take the CO2 at different times, time 2 minus time 1. Okay? You can get negative rates of change. That usually means that the variable is decreasing over that time. Positive changes, rates of change, mean that that variable is getting larger through time. Some of you said, well, my rate of change is really, really small. Well, it might be because we're talking about the change over a natural period of time. Okay, we're talking about the natural change in CO2, and then you're going to compare it to modern day. So they probably are very different. In fact, I know they're very different. We're going to talk about a little bit of that today. I'd like to show you this video here, which is a compilation of modern carbon dioxide with the ice core record, which is kind of what you're doing. It's an animated visualization put together by NOAA to help kind of visualize the changes we're seeing in carbon dioxide and the pace, the speed, the rate of change of those changes. Okay. So there's no sound, but what this is showing you is the amount of CO2 starting in the early 1970s, late 1970s, excuse me. And it's showing you the measurements across the globe. So South Pole, the Antarctic is on the left, excuse me, and the North Pole is on the right. And what we're seeing here is that seasonal cycle going from winter to summer, winter to summer. So we can see each hemisphere breathing, basically, as the plants grow and then go dormant during the winter season. And you can see that the northern hemisphere has more of a seasonal cycle because there is more land in the northern hemisphere with more vegetation for that seasonal cycle to have a bigger range in atmospheric drawdown, pulling up of CO2 during springtime and the increase in photosynthesis. You'll notice that as we move forward in time, we're now in 2015. The overall value of atmospheric CO2 has increased. We're now over 400 parts per million. And it's going to finish up here soon. in terms of that record, 2022. And now it's going to extend the record back in time through some of the early Keeling data from Mauna Loa in 1958. And now it's adding ice core data. So that data that you have been looking at in the homework, it has added that. So pre-industrial, about 278. And we're going to go further back in time now. Now we're going back to 20,000 years, 25,000 years, 40, 50, 60, 80,000, 100,000, 150, 200,000, 300,000, 400,000, 500,000, 600,000, 700,000, 800,000. Okay, so this is the record that you have been looking at, the ice core data. And let me go back here and pause it on this. And you may be able to, if you decide to do the bonus question, reconstruct this graph with the modern data, right? At the end, it's going to be a straight line up because the big picture here is the change in atmospheric CO2 has occurred over such a short time period that when you have all of the record, the whole ice core record, it's going to basically go off the scale. Okay. Now, big thing here is adding the modern to the ice core record. They're on different time scales, right? Modern day, we use calendar year. 2023 is a calendar year. The ice core record usually uses some time period before a standard. In the case that I give you, the data I gave you, it's from 1950 is time 0. That just standardizes it. So because if you just say years before present, well, every year you look at it, it's going to be a different present day, right? So we normalize it to 1950 or year 2000. So you have to convert the modern day CO2 record into the ice core age scale or the time scale. So you can do that by just saying, okay, if the ice core data is years before 1950, you can also turn modern data into years before 1950, but it's not going to be positive, right? All of this data is after 1950, so it would be negative years, which doesn't necessarily make sense, but it's how you could plot it all on the same one. Okay, any questions? All right. So you may have noticed there was no pre-work. There is no pre-work this week because I want you to focus, use that pre-work time to work on your homeworks, work on your project. Okay, so reminder, homework 3 is due tonight, homework 4, quiz 5, and your final project. So this is a busy week, all due on Tuesday. And these are going to be hard deadlines, okay? I've been pretty flexible with folks turning things in a little late if needed. You have that extension, but with the final project and these last assignments, I have to get your grades in. Okay, I'm on a deadline. I don't get an extension for turning in your grades. I have a hard deadline and I need time to grade your projects. Our TA, who just defended his PhD today, Chris, who's now Dr. McGuire, he has a lot going on and he's got to get these grades in too. Okay, so with that being said, everything's due on Tuesday. Your peer review. So part of your final project grade is looking at each other's presentations. Now, there's 50 of you registered in this class. I'm not asking you to look at and engage with every person's project. Rather, I've assigned each of you 7 of your classmates' presentations that you're going to review. That document is located under Files, National Park, Project Drawdown Final or Final Project, and then here under Peer Presentation Assignment. You'll find your name on the left and the 7 classmates that you're going to review on the right. Now, if unfortunately one of the people that you've been assigned to review doesn't submit their project, it's okay. You can find someone else's, just choose anyone else's and submit 7. So you just have to have 7. that has been, that form that you're going to submit is under assignments, under the final project, peer summary. It is a document and it's 7 tables, and you're just going to summarize what you've learned after looking at the 7 presentations, okay? And again, this is worth half of your final project grade. So it's not just about doing the work, but it's also about looking through and reading other people's work so that you are learning more than just 2 solutions to climate change. Okay, again, hard deadline. You have all day Tuesday and all day Wednesday to look at least 7. I would encourage you to look at more if you have the time, but I'm only asking you to go through 7. Okay, so that's 14 solutions plus the 2 that you did, so that's 16 solutions that you will have learned. Okay, questions, comments? It's crunch time. The end is close. All right, so today we're going to move on and talk about some of our past climate change, what we know the climate has gone through. We'll talk about our current state of the climate, and it'll lead us into solutions and what we can do on Thursday. Okay, so I want us to take a moment to look at this graph. This graph is called climate inertia. There are 4 colors here, each representing a different possible future based on how much carbon we emit to the atmosphere through fossil fuel burning. These graphs go up until 3000, year 3000. So we're over here in 2023. Take a moment, look at these graphs. Tell me what they're telling us. And I'm actually going to make it a little bigger. Sorry. It's a little small. There you go. Okay. What do we notice about this figure? What is it telling us? Mhm. Yeah. So what this is showing us, and we're going to look at more of these today, is a lot of times when we think about climate change, a lot of our discussions end at some time period, right? We usually say, by the end of this century, temperatures will do this. But it's important to note that the climate system, the Earth system, has inertia, and that the changes we're making today by our actions and our activities won't just end at 2100 when we make our forecasts or our projections. These different scenarios, we're going to talk about what they all mean today. But the reason the pink one drops off is because we've burned all of the fossil fuels. Like there's nothing left to burn. Okay. And so our carbon emissions drop off. We've run out of fossil fuels to burn. That's our high end, the worst case scenario. The middle panel, or panel B, shows you what happens to atmospheric CO2 concentrations with those scenarios. But what we see is that it will take a long time for those atmospheric levels to change because of this inertia, that there is the feedbacks in the climate system, that a molecule of carbon dioxide, once released to the atmosphere, can live and stay in the atmosphere for decades, hundreds of years, maybe even thousands of years, depending upon the feedbacks in our climate system. So that means our surface air temperature changes are kind of locked in for many hundreds of years. So what we're doing today, which can be a little scary to think about, what we do today, what our actions are in the next few decades, has long-lasting implications. And also, it means that just because we're not seeing an immediate change in the atmospheric CO2 level doesn't mean the actions we're doing are not meaningful. Okay, so don't let anybody try to gaslight you or fool you into saying, oh, if we, stop burning fossil fuels, the CO2 in the atmosphere didn't change, so it didn't matter. No, it's going to take a long time for all of the feedbacks that we've talked about to bring our system back to the pre-human kind of benchmark. And this is the idea of climate inertia, that the changes we see today, we've locked ourselves into some set change, but we can reduce bigger change by acting swiftly. Okay, so to tell you, we'll talk about our proxy records, what proxy records we have, how long they go back in time, to help us understand how much our climate has changed in the past. We'll talk about today versus then and what that could mean for the future. Okay, so using our different proxy records, right? We talked about speleothems, ice cores, corals, all of these different proxies have allowed us to reconstruct a history of Earth's climate. About 100 million years ago, the coral reefs grew much closer to the poles because temperature was much warmer. Sea level was about 100 to 200 meters, so that's like 600 feet higher than it is today. There were no ice sheets on our planet. Okay, so our ice sheets today are there because we were recently in an ice age. But there has been many times in Earth's 4.6 billion year history that we didn't have any ice on our planet. Global temperatures were about 6 to 14 degrees C warmer. Okay, so it has been warmer in Earth's history, but we also had a completely different climate system. We didn't have agriculture like we do today. Agriculture is important because we all have to eat to live. Why was it so much different back then? Well, the continents were in a different position. Remember we talked about those feedbacks, why climate can change? Well, if the continents were in a different position, that changed Earth's total albedo. Again, there's no ice on the planet, so that's changing Earth's albedo, and it impacted our atmospheric and ocean circulation, which is moving the heat around. Also, carbon dioxide levels were roughly 8 to 9 times higher than today, so almost 4,000 parts per million. Now, when we think about the carbon cycle, carbon can move around. And so we know that carbon dioxide is a greenhouse gas. When it is higher in the atmosphere, global temperatures are also warmer. Okay, so here is 500 million years ago on the left, going up until today. So this is a compilation of many different climate proxies. The left axis is showing degrees Celsius anomaly, temperature anomaly. And the right axis is showing degrees Fahrenheit temperature anomaly using the same baseline. So 1960 to 1990 average, just, what do you live in? I live in Fahrenheit most of the time, so I like to look at the right axis. So let's start on the right and go backwards. Most of the last 10,000 years, the Earth's climate, Earth's temperature has been steady. Yes, there's been some minor fluctuations before humans really came around and started doing industrial activities. Stable climate, important for agriculture, growth of farming. We go back to about 20,000 years. We're coming out of the last glacial, so temperatures warm up. Then we go back further to about 200 to 400, 800,000 years. We see the 100,000 year Milankovitch cycles going from cold to warm. Then we go back further in time. We can see that it was way warm 50 to 100 million years ago. Early Homo sapiens came around about 230, 240,000 years ago. So for most of Homo sapiens, evolution, climate has been quite cool. Earth's climate has been cool. So true or false? Atmospheric CO2 levels have been higher in the past than today. All right. So the answer here is true. Okay. Again, we as climate scientists are not arguing that CO2 is higher than it's ever been. It has been higher, right? So if we look at atmospheric carbon dioxide going back 100, so I'm looking at the bottom panel here, 100 million years ago, definitely it's been higher. It's been over 1,000 parts per million. It's gone down, it's gone up. And then you and I, we're hanging out here. We're about 423 or so parts per million today. So it has been higher. CO2 has been higher in the past. But the climate was much different back then. 25 million years ago, we have been able to reconstruct atmospheric carbon levels through using plant tissue. So there's different proxies, again, looking at how many stomata, the little pores in the plants, when they take in CO2, you can kind of figure out, do some linear regressions, trend lines, some of that data analysis that I've had you doing. You can look at the data and try to interpret what's happening. Anyway, they have showed that for about 23 million years, atmospheric CO2 has been relatively low. So here is the data for atmospheric CO2 on the bottom in green. It's kind of hovered around 350 to 300 parts per million. Again, we're higher than that today. So this proxy for reconstructing atmospheric CO2 shows that it was less than it is today. And again, we can't use ice cores past about 1 million years because ice did not exist on our Earth well back then. Okay, it was too much. It was warmer, and also the ice on Antarctica melts. It's moving. It's a glacier, and it's slowly moving and going out to the ocean, and it's lost forever. And 2 million years ago, looking at the last 2 million years, there's other proxies, and these are very busy graphs. Okay, and that's another thing I want to point out here, especially if you're not a scientist, if that's not what your interest is. As Zach mentioned, who did a great job of educating us on the importance of science communication, you cannot show this type of data to people. It's data vomit, okay? It's scary, and no one can really look at that and understand. So I encourage you, if you're interested in science communication and making a difference and being involved in the climate change movement, we need people that can help take this information, understand enough of the science to make it easier for the rest of us to understand. What I just want to show you is down at the bottom, okay? Just look at the bottom, the red. This is showing us the amount of carbon dissolved in the ocean, which is very similar to what would be in the atmosphere. Again, they're showing that over the last 200,000 years, the most carbon dioxide was about 300 parts per million. Okay, so pretty stable. somewhere around 250 to 300 parts per million. Okay. Now, for the past 2 million years, we can use ice cores. And I've shown you this many times. We can use those oxygen isotopes in the water, in the ice of the ice cores to reconstruct temperature change. And we see that as we move back in time, we have these changes, cold periods, warm periods, due to the Milankovitch cycles, the orbit changing, whether or not the axis is more or less tilted. Where is the axis tilted towards in our orbit, that precessional change? And again, all of these work together in feedbacks. Okay, so climate changes over the past million years. Okay, this is the ice core record. The top in blue is the amount of CO2. This is a direct measurement using the air bubbles trapped in the ice. The black is temperature anomaly, measured from the oxygen isotopes, and the red is methane. What I'd like you to do here is, for a moment, look at the range. How much change is there in CO2? What's the lowest amount of CO2 measured over this 800,000 years? What's the highest amount of CO2? Also do the same thing for methane. What's the lowest amount of methane, which is in red? What's the highest amount of methane? Let me know. Yep. So if we're looking at the lowest amount of methane, or excuse me, let's start with CO2 in blue. You know, the lowest amount is maybe somewhere around here, maybe about 170. So CO2 is about 170 to maybe upwards of 300. Okay. Then methane, the lowest methane is also kind of around the same time as the lowest CO2. We're looking at maybe about 350, going upwards of 800 parts per billion. Okay, so it's 1,000 times less abundant in the atmosphere. Okay, those are the ranges. And they're pretty consistent, right? So for 800,000 years, methane and CO2 moved between those values and didn't exceed them. Okay? And we'll look at what that is today. So during the last glacial period, about 30,000 years ago, oops, wait. Yeah, about 30,000 years ago, temperatures were about 4 degrees C cooler on average. We had large ice sheets covering the Arctic. We had the Patagonia ice sheet, and sea ice extended all the way to about 30 degrees north and south. So like if you're flying, if at that time you flew an airplane, you'd be flying mostly over, like going from New York to London, you'd be flying over sea ice most of the time. And that's not true today, right? Global temperatures are much warmer. So what's happening during our global ice ages? What is happening to the sea level? Is it increasing, decreasing? All right, during glacial periods, when it's colder, we have more water stored as ice on land, as that land ice. And so global sea level is much lower. okay? Because we're exposing more of the continental shelf, the area around our continents, and so our continents get larger in terms of surface area. Okay, so sea level during the last glacial maximum was about 120 meters lower, or about 400 feet lower. And so here's Florida. Okay, Florida is facing many issues right now in terms of sea level rise because of climate change. But 30,000 years ago, during the peak of the last glacial period, last ice age, this black line was the coastline of Florida. So it kind of gets smaller and bigger as the sea levels are changing. And this map here, all of these red areas show you extended coastlines during the last glacial period. For example, here, if you look at Indonesia, you can see a lot of those regions, it was much larger land mass. It's not so many islands anymore because the ocean level was much lower. Now, what this means was really interesting in terms of humans too, right? So at that time, during the last glacial maximum, Asia was connected to North America via the Bering Land Bridge because that area was exposed, the water had dropped. And so it is thought that there were many human migrations across North America through that time, which is really interesting in terms of humans and ancestors. Also, because it was so much colder and we had ice much further south in terms of its extent, it was closer to the equator, all of our vegetation belts were shifted southward. Okay, so now what we consider tundra and cold weather conifer was very close to, say, the Gulf of Mexico. And now all of those regions have moved northward. Okay, and so that's what we're actually starting to see is the opposite of this today, is that our temperate deciduous forest can move further and further north because it's getting warmer today. Okay, so the tundra limit, what we consider tundra, was about 48 degrees north during the last glacial period, and today it's well above 68. So a 20-degree latitude shift in our vegetation belts. Okay, other really cool things about the last glacial period is a lot of our fauna, animals, were adapted for extreme cold. They were much different in size, and modern humans were finally on the scene. Now, as we move out of the last glacial period, so the last glacial period kind of ended around 20,000 years ago. 20,000 years ago here, our temperatures increase slowly. Okay, we're talking about 3 degrees over 10,000 years. You'll notice this blue line here, temperatures are pretty stable. This is known as the Holocene in geology. It is the current interglacial, the current warm period of Earth. And because of this stable climate, we as humans have developed agriculture and civilization as we know it. We can grow foods, we can grow different types of foods in different regions, and this is what we know because this is the climate that we've had for thousands of years. Now, of course, you can see the red line right at the end. That is temperature change projected out to the end of the century. Okay, we're not all the way up at 3, we're at 1 right now. Okay, but you can see that rapid straight up at the end. But if you notice a little bit of a trend in that blue line, that's because we've actually, if you look at the long term over the past 2,000 years before industrialization, so going from basically calendar year 0 up until about 1700, so 1700 years, Earth's temperature was slowly decreasing because Earth was starting to head back into an ice age. Okay, but humans have now altered that through human activity and pushing more carbon into the atmosphere from the solid Earth reservoir. Okay. I don't know what that is. I've lost an image, so I can't really have you answer that. But the main takeaway here is that the world has been warmer and colder in the past. Okay, again, climate scientists are not arguing that this is new per se, right? We're not saying Earth has never been colder or never been warmer. What we're arguing is that the plants and animals, our flora and fauna on our planet, excuse me, has adapted to our current stable climate. And I should say current climate of the last several thousand years, minus the last 200, because that's been a rapid change. What is concerning and alarmist, why we are waving our hands and saying we need to do something, is that the rate of climate change is unseen before. We've never seen the change that we are seeing today. Okay? It is happening hundreds of times faster than what we've seen in our records. And that's the problem, is the change is so fast, we have nothing to compare it to. We don't know how certain species of plants and animals are changing now or may change in the next 20, 30 years because we have never seen this before. Okay, so this is an example. So this is kind of from your lab. It's not exactly the same data set, but it's very similar. In your lab, you're asked to calculate the rate of change in the historical record from the ice cores. Okay, so the change in CO2, the delta, that symbol means change in CO2 over time. We get a number, again, this is not exactly the same data set as your lab. I'm using maybe a different time period, but very similar concept, is about 0.0034 parts per million per year. That's historically. When the Earth is changing climate because of changes in our orbit, that's how fast atmospheric CO2 would change. We can see that. We've measured it in the ice cores. Now today, atmospheric CO2 is not changing linearly, it's actually accelerating. And that's something else you'll see in your lab, is when you calculate the rate of change over different decades, they're not the same. The change is happening faster in the more recent years. And you probably already saw that in the first lab where we're looking at temperature. So CO2 and temperature are linked. They are correlated. In fact, they're causal, meaning an increase in CO2 causes an increase in atmospheric temperature. We know that to be true. Modern change in CO2 is about 2 to 3. It's more like 3 now, closer to 3 parts per million per year. That's more than 600 times faster. 600 times. Okay, what does that mean? I mean, 600 is a lot. That should be enough. But if you need more, if you need another analogy, imagine you walking around Ring Road. Okay, you're going, I don't know, to Starbucks. Okay, you're walking, maybe you're walking about 3 to 4 miles per hour. And this ginormous Lockheed Blackbird flies past you at its top speed of 2,100 miles an hour. Not in the sky, I mean literally next to you. That is modern climate, your historical climate. And that is why we want change. We need change in our society because it's happening so fast. The change is happening so fast. Okay, so how's our climate changing now? I just pulled this data from NOAA a little bit ago. So they gave us some updated values for July. So of course they're not giving out data immediately because they have to go through and quality control it, make sure there's no issues with the measurements, and then they publish monthly updates. So this is for July. It was published on August 5th. And so they'll probably be publishing August in the next few days. Here's our Keeling curve showing atmospheric CO2 increasing. And when we compare the years, this year's July global average was 422.14 parts per million. July of last year, when I taught this class, or taught a similar class, was 418.85. So almost 3. Or wait, yeah, 3 parts per million. Okay. So again, I've mentioned this many times. The Intergovernmental Panel on Climate Change, IPCC, who I've used many, many, many figures from this organization for this class, should be the first place that you look for information related to climate change. Share it with your friends, share it with your family. This is the leading organization on climate change. It's part of the World Meteorological Organization, part of the United Nations Environmental Program. It's part of the United Nations. The whole group in 2007 won the Nobel Peace Prize for their work on global climate change. And when I say group, we're talking thousands of people involved in these projects, in these reports. Okay? Openly peer-reviewed by the scientific community, which means anything that's going into these reports has to be signed off. Everybody on those chapters, the hundreds of authors that are putting their time, volunteering their time, they're not getting paid for this. Okay, scientists, we're not making money. I mean, we're not rich. Most of us are not that rich, okay? They sign off if they agree with everything that's said in those statements, in those summaries. The scientists and the governments. So these are intergovernmental. So it's both scientists and policymakers for over 120 countries. You can check out their website. All of their reports are publicly available. Okay, it's all here. They have some interesting graphics you can look at. All their reports, you can click on reports. The most recent one, the annual assessment number 6, climate change 2023. You can look at what should we expect if global warming gets to 1.5 degrees C, etc. Okay, so this is where to go. If you have questions, you can download all the reports if you want. Okay, the next resource for climate change information that's a little bit more user-friendly, right? It's not so dense, it's not so scientific. It is scientifically backed, but it's more for your uncle who maybe watches too much news, okay? This is called Skeptical Science. I really like this website. It's, again, run by scientists, so it's not glamorous. It's not the most, developed website, but you can click on anything you want, right? For example, they have some of the most used climate myths, right? Climate's changed before. That's the #1 myth that is used to argue against human-caused climate change. So you can click on this myth and you can be told basic information about what the science says. And you can click on intermediate. It goes into more depth. There's diagrams and see, that one might look familiar, right? And all types of information. So what I want you to do, okay, if you've taken this class, is anytime somebody says something that is not true, and you know it to not be true because you took this class, you're going to refer them to skeptical science. Because we learned on the first day of class, the main issue is not that people don't know about climate change necessarily, it's that we're not talking about it enough. Okay, so we need to talk about it, we need to share information, and not in a condescending way, right? We just want to make sure people understand because there is a lot of misinformation. There is a lot of money involved in lobbyists and lobbyist groups because people are making a lot of money right now on our current industries and way of life. And we'll talk about the Green New Deal and some of our policies on Thursday. But just keep that in mind, right? There's people getting rich still off the back of our planet and the lives of other people. Okay, so climate change, it's not just a science issue. And it's not just an Earth system science issue. When we talk about climate change, we're talking about the well-being of people. And you can sit here for a moment and look at where your interests lie. What is it that you want to accomplish for your career? What are your long-term goals, right? Maybe you want to be a doctor. Now, in 30 years, our climate is going to be so much different that we're going to see changes in disease. And we're going to talk about that. We're going to see changes in heat waves and drought, which will impact people disproportionately across the globe. Okay, so I'm going to take a break here, and I want you just to think about where your interests fall and how you can be sure that you're going to make a difference in the climate change issue, because it's not just the science issue, it's a societal issue. Every single one of us are going to be impacted in some way by our changing planet. Okay, let's come back at 2:30. 2:30. I'll see you then. All right, so we will continue on here, and we're going to talk now about what's happening now. What are some observations we have made that let us know that the climate is changing in the past few hundred years? So I'm going to call these the big five. These are the big five indicators that our climate is changing. And we'll go through each one in detail, but they are: 1, the surface temperature is increasing. 2, the global average upper ocean heat content is increasing. The summer Arctic sea ice is decreasing. Our ice sheets, our glaciers, and our snow globally is decreasing, and our sea level is rising. So what is happening, right? So we come back to the big picture radiation budget. How much of the sun's incoming energy does Earth receive? How much gets sent back? What's really happening right now is this layer, this greenhouse gas effect. The greenhouse effect where we have more outgoing infrared energy from the Earth getting trapped because we have more of those greenhouse gases. So we're essentially adding more blankets to our planet. You add more blankets and more blankets, that planet is going to get warmer. So our global temperatures are increasing. If we look at the global average temperature anomaly data set, which you've already done, we can see that the atmosphere has warmed by about 1 degree Celsius since the 1950s. And again, when we think about change and long-term change, climate, when we think of climate, climate is usually about 30 years. You can't use shorter data sets to really drive trends or to conclude trends because there is interannual variability, as Zach mentioned, with some of the changes in sea ice, right? Weather versus climate. So when we think about trends, we want to think about long-term change, 30 plus years, because some years are warmer than others. For example, in this data set, this year in 2018, 2019, here I'm going to circle it, was pretty warm. Anyone know what that year happened to be? Why was it so much warmer than the year before? What's something on our planet that makes things warmer? We talked about it. It's in our ocean. Yeah, El Nino. Okay, so El Nino years, when we look at them, they are warmer. So then this year right here was also a bit warmer. That's the 1998, 1999, or excuse me, 98, 97, I believe, El Nino year. We're in another El Nino this year. So it's very likely that this year will be much warmer than the last year. But partly that is due to the internal variability that we see from things like the El Nino Southern Oscillation. And it's likely hotter today than it has been in any time in the last 1,300 years. It's also very likely that this year will be the coolest year of your lifetime. Something to think about. Okay. So our global temperatures are increasing, not everywhere equally. So this image from the IPCC shows the observed change, what we've actually seen happen in global surface temperatures between the period 1901 to 2012. Where is the greatest warming? Where's it been? All right. So we see first is that the Arctic doesn't have much data. That's partly due to the fact that we're talking about 100 years worth of data here. We didn't have satellites looking at the North Pole, the Arctic, or the Antarctic back in 1900. Okay, so that's only a subset of this data. So when we look at the rest of the data that we have available via instruments, via our thermometers, land-based thermometers, shipboard thermometers, we see that most of the extra warming is occurring all over the land at higher latitudes. Going back to the principle that land has a lower specific heat. It takes less heat to change land temperature, soil and rock, than it does to change the temperature of water. Now, water is warming, and we're going to see that, but not the same total change. In the future, we're never going to have extreme cold weather events. True or false? All right. The answer is false. Okay. So when we think about climate, if you've ever taken a stats or statistics course, basically most data will fall in what we call a bell curve. Okay, it's like this curve here. And the average, what we call the average, is that 68% of the data is falling along that value, near that value. Then you have extremes. And those are the data points that fall either on the low or high end of that set. Okay, so here's our bell curve. Most of our data is falling around the average. Then we have some cold days, some extreme cold days, and we have some extreme hots. What we're doing with climate change is we're moving the whole data set, all the temperatures on Earth, we're moving them to the right. We're making them warmer, which means we will see more hot weather and more extreme hot weather. We will still see extreme cold weather events, but they will just be less frequent because there's still going to be cold on our planet, right? There's still going to be months where the North Pole is in darkness and months where the South Pole is in darkness. So there's still going to be that unequal heating of our planet. It's just we are trapping more outgoing heat. And so we're moving the whole average to the right. And so those colder times will become less frequent, but we will still have them. Okay? They'll just become more infrequent. So our next observation that our temperature or our planet or climate is changing is that our oceans are warming. Okay, and remember that ocean, that water, takes more heat to change temperature. That's the specific heat of water. Right now, our oceans, because they have the potential to absorb so much heat before changing temperature, that's the thermodynamic, property of water. It's just an amazing, amazing thing we have on our planet. It can absorb so much heat. Our oceans have absorbed about 90% of the excess heat in the climate system over the past few hundred years. And so when we look at the sea surface temperature, taking measurements of the ocean all over the world for the past 150, 160 years, we can see that temperature is increasing. Again, these are temperature anomalies comparing a baseline every year to that baseline. What we see is that global surface temperature of the ocean has increased by about maybe 0.3 to 0.4 degrees Celsius. And that's about half, a little less than half, excuse me, a little more than half, no, a little less than half of what the atmosphere has warmed. Because the air versus the ocean effect, right? The air is going to heat up faster, the ocean will heat up slower when you apply the same heat change or extra heat. You can also take a measurement of the amount of heat in the ocean, which is what we call heat content, and we can see that that is increasing quickly. Now, what does that mean in terms of some of our ocean and our ocean life? Well, we have seen coral bleaching. So corals are living things, they're living animals. And coral depend on algae to survive. Okay, this is a very symbiotic relationship. If stressed because of temperature change or salinity change, the algae will leave the coral, and the coral no longer have kind of that protective surface, and the coral become bleached, they become white and vulnerable. So the color of our corals is due to the algae themselves. And this is an older stat, but still very important nonetheless. This is showing the Great Barrier Reef off the coast of Australia. The reefs near the equator, closer towards the tropics, when surveyed several years ago, over 81% were severely bleached. And that's because ocean temperature is changing. And coral are just very sensitive to change in temperature, so are those algae. And even just a few half degrees here and there really make a difference. Okay, so again, here's the situation. The coral and algae depend on each other to survive. They have that symbiotic relationship with an algae called zooxanthellae that live on their tissues. They give the coral food source and they give them the color. And when stressed, that that algae leaves. Okay. And the coral is left bleached and vulnerable. It loses its major source of food and it turns white or pale and is now susceptible to disease. So it's not just an ocean temperature change that can cause coral bleaching. It's things like pollution, too much sunlight. So if the ocean level fluctuates too much, that will impact the coral. For example, extreme low tides when the water level drops. Our third indicator that climate is changing is our Arctic sea ice is decreasing. Okay, I'm not going to go too much into this because Zach did a phenomenal job looking at what we know and what we don't know about the Arctic. And what we know is from satellites since the late 1970s, we can look down on Earth's poles and see how much sea ice there is. And we can see that it's decreasing a lot. Okay, and this is some figures that he's produced. Why it matters is that very critical ice albedo feedback we've talked about many times. The sea ice is super bright. When you replace sea ice with dark ocean, you change that local albedo. The Arctic is warming faster than the rest of the planet because of that local albedo feedback. Also, the amount of older ice is getting lower. We are losing that multi-year sea ice, and multi-year sea ice is harder. It's less likely to break apart and expose open ocean. And so we look at this data set from 1985 through 2018, so it's already 5 years old now. 5+ year old ice in red, hardly any anymore. Most of the ice we have now in the Arctic is 1 or 2 year old ice. So it's much thinner. And that impacts sea ice volume, right? So extent plus thickness gives us volume. So there's less total ice in the Arctic. Number 4 is that our ice sheets, our glaciers, our snow is decreasing on our planet. You can look anywhere and you can see it. So if we look at the snow line, which is how far down a mountain the snow can exist, those snow lines are increasing because as you move higher up, temperature decreases in our atmosphere. And so the snow has to go further up. Like it can only exist where it's cold enough. And you can see in Kilimanjaro, that snow line has to go very high. So not much snow left on some of these very tall mountains where there should be snow because it's usually cold, not that cold anymore. Our glaciers, one of the best ways of looking at glaciers and their change is through time-lapse photography. We can look at the Muir Glacier here on the right in Alaska in the early 1900s, mid 1900s, and early 2000s. And you can see just how much it has retreated, moved back up into the mountain, higher slope, upslope, to find those colder temperatures to where it's not melting. And as Richard Alley said in the video from a few classes back, glaciers globally, one glacier can tell one story, but globally, all the glaciers are going to tell the story of climate. And globally, I think it's over 90-something percent, 95% of our glaciers are decreasing in size. Also, the things that make a lot of news are when big icebergs break off of our ice sheets. Now, icebergs are already floating in the water, okay? It's the floating part of our ice sheets. We call them ice shelves, right? So when the ice comes off the land and is now floating in the water, we call those ice shelves. They break apart, you get icebergs. Now, it's very sensationalized because these are huge pieces of ice, you know, the size of Chicago or the size of Manhattan has come off of Antarctica. Why that matters is not so much for immediate change in sea level, because these pieces of ice are already in the ocean. What matters is that these ice shelves are helping to keep the ice on land on land. We call this a buttressing effect. Okay, so here on the bottom left, if we look at what's happening beneath the surface, beneath the ocean, those ice shelves, this portion of the ice in blue I'm shading, kind of it gets stuck on some rock underneath, some soil, some topography underneath the water. And they act to hold back the ice. The ice is flowing, and if there's a lot of friction because that ice shelf is being grinded against rock, it will keep the ice sheet from flowing as quickly out to the ocean. We call that a buttress because if you look at architecture, our beautiful grand cathedrals have these buttresses. That's the way the walls are held up in these cathedrals. And so the ice shelf, what's in the water, is holding back the ice sheet. When these start to collapse because the water is so warm and they just start melting these giant chunks of ice and they're breaking off and becoming massive icebergs, then our ice sheet starts to flow more rapidly into the water. And that is contributing to sea level rise. Okay, number 5, sea level rising. We can look at all of the data we have across all of the world, and we can see that global average sea level has increased by nearly a foot. And again, this is an average. Some places are seeing more change, some are seeing less. But again, the big picture story is what matters here. Now let's go back to our topic of cryosphere. Remember, there's 2 components to the increasing sea level. There's the fact that we're adding mass to begin with. We're taking the melting land ice, the melting cryosphere, and we're adding mass or adding volume to our oceans. That's rising the sea level. What we're seeing today, 75% of sea level rise is due to the addition of more water to the oceans from that melting land ice. The rest, the 25% that's remaining, is due to the fact that the oceans are getting warmer. And that's what I showed you in my little volumetric flask, which I still have here. There's no water in it though, because a little baby loves things like this. Okay, so in my volumetric flask, we saw that when you heated the water, the volume got bigger. Okay, that's our sea level rising. So a combination of both of these factors. Other changes to our ocean is the ocean acidifying. And we talked about this and we talked about our oceans in the carbon cycle. When you add more carbon dioxide with water, you get carbonic acid. And we can see our oceans are absorbing more carbon dioxide because atmospheric levels are increasing. Those systems are trying to buffer, they're trying to be in balance, and therefore our ocean pH is decreasing. Now, when we look at coral reefs, these are calcium carbonate forming organisms. The amount of carbon, carbonate, and the different ions of carbon, bicarbonate, etc., that ratio changes under different pHs or different acidities or levels of carbon. And we can see here's a beautiful coral at 375 parts per million carbon in the atmosphere. As you move to 450, which is where we're pretty much at now, and as we move to 500. They will not be able to make the calcium carbonate shell. They will no longer exist. They will die. So other changes, those are our big five, but there's many other things that we can look at, right? We can look at shifts in our precipitation patterns. Places that have had rain that usually are wet will get wetter. Places that are dry will get drier. So more extreme flooding, more extreme droughts. Some other changes that we see include our ecosystems. When we think about the big picture, we are noticing and can observe changes in the timing of seasonal life cycle events, migrations, hatchings, the cherry blossoms, right? We have hundreds of years of records of when the cherry blossoms bloom. And we can see that those are changing. It's becoming earlier in the year because temperatures are warming. The range of insects, range of critters are changing. Where they can live is changing. Our food webs are being disrupted. And one that's really important is parasites and diseases. Mosquitoes, they are able to move to different places. Their range of where these mosquitoes can exist is changing, which means different viruses like the Zika virus or the West Nile virus are expanding. More people are now exposed to West Nile. In fact, here in my city in Colorado, we just got a notification from the city that someone died from West Nile. That's scary. Okay. Pine beetles, this is something that impacts California big time, is these pine beetles infest our forest in California and they kill the trees. Well, dead wood, dead trees are very good fuel for the fires. So disease shifts. So it's always important to note who's doing this work. So I want to highlight my good friend and former UCI graduate student, Dr. Morgan Goris. She's now a research scientist at Los Alamos National Laboratory. And her work is focused on looking at these disease spreads, where they're changing, and how climate change will impact where these diseases are going. So her work looked at valley fever, which is a fungal infection that you can obtain from some spores in soil. So really, in 2007, most of the valley fever cases were found in the southwestern United States. A lot of people that got infected with valley fever were construction workers, agricultural workers, people that are out impacting, stirring up the dirt. If untreated, it can be deadly. Most of the time, the symptoms are flu-like, which, okay, everything's flu-like. COVID's flu-like. I just went through that. So what happens when you go to a doctor and you say, I have flu-like symptoms, and they don't know what you have? They can't treat you. And so what she has discovered is talking to the health centers and the communities is that places that are starting to see more valley fever cases, the doctors are not trained because they might have been trained on the East Coast, which valley fever is not an issue there. And as we move forward into a warming climate, she sees that the range in valley fever will go all the way north and it will even expand into Canada because it's based on soil temperatures. And it's not just about, the land, and it's about people too, right? We have to think, and, we talk about why are we so bad about thinking about climate change? And we can't just talk about the planet, the planet, the planet. The people are on the planet. You and I are living on this planet, and we are seeing the impacts, and our lives and our well-beings is what matters. And it's not equal. Okay. Here is a graphic showing the winners and losers of climate migration. This is showing where people will be moving to and from by 2080 based on changes in temperature and how much each city's economy will be impacted, right? So New Orleans, Louisiana, it's sinking. Sea level's rising, prime hurricane country. They anticipate that over 500,000 people will leave this region, which will impact the gross domestic product or GDP, the money economy, by about 10%. So it's, you can figure out a way to talk to anybody about climate change. If they're in the money financial sector, well, it's about money. Where are you going to build homes? Where are people going to want to live? If that's how they want to think about climate change. And also climate refugees. People are already having to evacuate and move away from their homes and their way of lives because of climate change. And so this map shows places in the world that are impacted by hurricanes or tropical cyclones, impacts of desertification, small islands that are impacted by extreme weather and rising sea levels. And we can see that every continent is impacted. And not every continent has the same means by which to mitigate or adapt. And so that means many people in our world will have to move or be evacuated. And then it becomes an issue of where do people go? So already this is happening in the United States. In Alaska in 2009, 12 villages of indigenous communities were relocated because of coastal erosion and issues along that lines. In Louisiana, a native population is being depopulated, that region is being depopulated. They're moving this whole group of people because the sea level is rising and they can no longer access their homes. Currently, no government framework really exists for the aid of climate refugees. Right? We have frameworks for refugees for other issues, war, for example, but not for changes in climate. If we look at the world, a really unfortunate example of climate refugees would be Bangladesh. So Bangladesh is a river delta. It's basically only exists because the rivers have deposited a lot of sediment in this area, but it can't keep up with the rising sea level. And by 2050, so in the next 30 years, less than 30 years, it's estimated that 1 in 7 people in Bangladesh will be displaced by climate change and the rising seas. Okay? And so the question is, where should and will these people go? Now, I am a physical scientist. I am not a social scientist. I'm not a political scientist. And that is a question that is well beyond my training, but it is a moral question. Where do people go? Who helps them? Who helps them when these people aren't necessarily to blame for the changes that have impacted them? We're going to talk about the inequities of climate change on Thursday. Not everybody is contributing the same to climate. Not every country has contributed the same to climate change. Who's responsible? Who should help? Who should fix it? Okay. Which of these, if you're still with me here, is not a cause of climate change? And B is, or excuse me, C is showing us sunspots. All right. So the answer is actually D. Okay. So A is Milankovitch cycles. That is a way our climate can change naturally, changing the amount of incoming sunlight the Earth receives. B is a volcanic eruption. Volcanic ash, the different particles that are released during these big explosive eruptions can impact our albedo. They send incoming sunlight away and can temporarily cool the planet. So they can impact climate. And over many millions of years, the CO2 emissions from volcanic eruptions have changed our greenhouse effect. C, sunspots. In our first lab, I asked you to write a rebuttal about sunspots. And sunspots do impact the amount of sunlight Earth gets by a small amount. Okay, so they are a small change in our climate. Not a big one, but of course, if you have many, many years combined of lots of sunspots, that would impact our climate by changing the solar luminosity. D, the ozone hole. This is a success story, actually. We're going to talk about this on Thursday. The ozone hole is very much a UC Irvine history lesson, and we'll talk about that. But the ozone hole does not have anything to do with climate. In fact, it has to do with human activity. How humans created something that we thought was good. Turns out it wasn't. And it impacted our planet pretty badly, but we were able to do something about it. And we'll talk about that success story. So why is our climate changing today? And hopefully by the end of this day in this class, you know this off the top of your head. You don't even have to think about it. Greenhouse gases, right? When we look at, again, these, you've seen this before. This shows you the forcing, how much extra heat or how much cooling these different components of our climate system are contributing. Our greenhouse gases are the big ones. So looking at that, how much extra warming on Earth is happening due to our greenhouse gases? Alrighty. So when we look at these graphs, you got to look at everything that's being displayed. So of course we have the top part here, greenhouse gases, is telling us that anything beneath us is a greenhouse gas. So on the left, we have CO2, methane, nitrous oxide, and halocarbons. Together, they're about 2.5 or so, 2.6. But we also have the tropospheric ozone, which we haven't talked about, and it's just not as important necessarily as the big ones, CO2 and methane. but you have to add that contributor as well. So it's more like about 3 watts per meter squared, which if we remember going back to the beginning when we figured out how much of the sun's energy Earth receives, every square meter, if you measure out a square meter, about 3 point something feet, every single meter of our Earth gets about 342 watts per square meter. Currently, human activity is adding an extra 3 per square meter. And that number is increasing because we're adding more carbon to our atmosphere every single day. Okay, so something happening really interesting right now, and you might have heard me ask Zach about this during the presentation he gave, is that Antarctica is seeing the most unbelievable minimum in sea ice ever. Okay, so all of these lines here are all the years of data from 1989 to 2023. So nearly 40 years of data. And this year is red. And so we see that there's a very, very unusual amount of change. And if you do the calculation, the statistics, this is something by statistics occurs only once every 1 in 13 billion years. The Earth is only 4.6 billion years old. So this is really amazing. Okay, so just to summarize, our Earth is changing, or excuse me, our climate is changing rapidly. And many factors control our climate. We've talked about a lot of these factors, but the main reason today is the greenhouse gases, especially carbon dioxide. Those gases have increased in our atmosphere due to the anthropogenic or human burning of fossil fuels. And why have we used so much carbon dioxide? Well, it's because of our extremely rapid population growth and our corresponding increase in demand for energy and resources. All right, so let's just see where we're at. So now we're going to switch to a little bit of a different topic, and we're going to talk about how we can forecast or project future climate, and what are some ways that we can prevent the worst case scenario. Basically changing our lifestyles. What are those ways? What can we do? Okay, so how and will climate change in the future? We have to use climate models, complex computer models, which take these different processes we've talked about, like the albedo ice feedback, and create mathematical equations that can best simulate that relationship. And we put those into these computer models, and these computer models are solving those mathematical equations on grids. Okay, so think of the Earth. Here's our Earth. It's round, it's a sphere. We divide the Earth into different horizontal grids, basically by latitude and longitude, so we get squares. And then we take the atmosphere and we divide it into layers. Then we also take the ocean and we divide it into layers. So it's a 3-dimensional process. We include our knowledge and understanding of the land, the atmosphere, the ocean, the ice, the cryosphere, the biosphere, water, energy, all of the cycling of the nutrients, the carbon, the methane, all of that, everything we know. And so as we are continuously researching our planet, new information can be added to these computer models to make them even better. When we think about future climate, what is the most uncertain or unknown factor about future climate change? All right. Now, all of these things have some unknown or uncertainty to them. The most uncertain is human activity because humans are chaotic. We can make changes, we can make decisions, and that's not something you can put into a model. We don't really have mathematical equations that can describe humans. Okay? The first publication of the greenhouse effect, the concept of adding more carbon to the atmosphere, more methane, more CO2, impacting temperatures is very well known. Okay? The first publication of this feedback is in 1896. It was actually discovered many years earlier by a female scientist, Eunice Newton-Foote, who concluded in her experiments that CO2 increases would cause atmospheric temperature change. But as a female back in the mid 1800s, she wasn't allowed to publish her findings. And it was a few decades later that others were publishing that work. But we've known about the greenhouse effect for many, 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 many years. That is well known. The uncertainties really are how is cloud and precipitation changes going to impact our atmosphere and our climate? We know generally that warmer temperatures mean more evaporation, maybe more clouds. Where are the clouds? Are they high? Are they low? We've talked about how the difference in where they are in the atmosphere can impact temperature change. So that's a little bit uncertain. We have sudden shifts in the climate, like our ocean circulation, our sea ice. Of course, that could be fast, and maybe we don't get it perfect in our models. Of course, how much ice sheet volume loss are we going to have? Okay, but the biggest uncertainty is humans and what we're going to do. And so when we think about future climate, we have to create some scenarios of what could we expect if we do X, Y, and Z, and what can we expect if we do A, B, and C? Okay, what is that range? And so we use these representative concentration pathways, also abbreviated as RCPs, and these are plausible greenhouse gas trajectories using our understanding of economic growth, energy sources, population growth, how much renewable energy we switch to, etc. Okay? And we have basically 4 major RCPs. And each RCP is numbered. So for example, RCP 2.6 lets us know that by the end of the century at 2100, this concentration pathway would result in a total change in radiative forcing of 2.6 watts per meter squared. Okay, so that's how much extra warming the Earth will receive because of increases in carbon and methane, or CO2 and methane, excuse me. Here are those 4 scenarios shown on the right. I don't have them labeled here, but you could probably see some result in radiative forcing starting to go down, and one is basically continuing without stopping. So these models, these pathways, include what's going to happen with population, right? So we can make some guesses. All of them basically show a leveling or a slowing down of population growth. The population will continue to grow, but not at the same rate. What type of energy are we going to be using in the future? Well, we can make guesses. And each of our scenarios, for example, RCP 2.6, RCP 8.5, and there's some in between, show a range. How much coal will we use? How much natural gas? How much hydroelectric? So we can run our models with different inputs for these energy sources. Here's our CO2 emissions for each of our scenarios, and I'll let you know, here's the scenarios. RCP 2.6, 4.5, 6, and 8.5. I don't have them labeled here, but we'll talk about it. Which of these future CO2 scenarios do you think is most likely, given our current economy and lifestyles? Well, I didn't tell you which is which, but here's the thing. We know that temperature change and the amount of carbon in the atmosphere are linearly related, meaning when you increase one, the other will increase. So you can probably tell which line goes to which. Alrighty. So we've already passed the 2.6 RCP scenario. We're right there. Okay, RCP 2.6 is the green line here, meaning that as of 3 years ago, we would have had to start reducing our carbon emissions. And this is not just in the United States, this is globally. We share our atmosphere. What we do in the United States matters. What, people do in Europe matters. So globally, we would have had to reduce our CO2 emissions starting several years ago, and we have not done that. The blue line is RCP 8.5, which is basically like we continue on. Eventually, in the next 60 years, we'll do something. And that's basically using up all of the carbon, using up all the fossil fuels. Okay, so here's our current track. We are currently somewhere, we've kind of slowed down a little bit in the past few years. This is now almost a 10-year-old figure. We are between the 6 and the 8.5. You'll notice there's the solid, the darker red, brown, yellow, and blue. Those are the model averages or model means. So when we run our climate models, we don't just run it one time. We run it hundreds of times, thousands of times to see how small changes in population change or small changes in the proportion of fuel sources, how that impacts the end result of, for example, carbon emissions. And so the red lines are the solid lines are the average of all of those scenarios. So historically, we were following the red. We're kind of a little bit lower than the red now, but we're still on par as of today for over 2 degrees Celsius of warming, which is not great. Okay, so again, the RCP 2.6 scenario is we had to kind of start cutting down, and eventually we'd have to be in negative global emissions, meaning we're no longer emitting carbon, and in fact, we're taking it out of the air. And we'll talk about that tomorrow or on Thursday. So what can we expect? So when we look at our models, we're going to look at the low end, the 2.6 scenario, which is the lowest end we modeled, and then we have the highest end, which is kind of unfortunately where we're at, what we're on, the trajectory. So here's an image from the IPCC's recent report, the previous report, but it shows the change in average surface temperature between the late 20th century and then the late 21st century. And on the left is the RCP 2.6 scenario, and on the right is our RCP 8.5 scenario. What does the data suggest? What do the models suggest would be the difference in temperature over the Arctic between our two scenarios? All right. And this is not the best graph. And this is another reiteration of the point that we need help with data visualization. So as Zach mentioned, how can you visualize this better for people? Because I can't necessarily tell the difference between that brown and that red, right? It's hard. and we need to do a better job. But what I would say is it's going to probably be, C to D, either 5 to 7 or more than 7. It's not perfect, but this is important. And we can make a difference in the total change. We've already committed to some change. We're already seeing it. The Arctic has seen changes for the past decades, but how much extra depends on which path we take. Okay, so warming is not distributed equally. That Arctic amplification is going to cause the Arctic to see much more change than the rest of the planet. Again, we can look at the differences in precipitation patterns. The low emission scenario on the left, the high emission scenario on the right. We see that on the right, more extremes, more dark colors, more light colors, so more floods, more droughts. What about our what about our sea ice? The left is showing the amount of sea ice in February. The right is showing the amount of sea ice in September. The different colors are the different models, scenarios. So RCP 2.6, RCP 8.5. On the right, what is concerning is that the observations, what's actually happening, the green line is we're seeing a decline in summer Arctic sea ice extent that is faster than our models suggest should happen, which means that Arctic amplification may not be as well represented or understood in our models, right? So that work that Zach is doing to understand Arctic climate change is really important so we can add it to our models. How much will sea level rise? Again, how much land ice is going to melt? How much extra heat is the ocean going to absorb and then expand? Well, here's our scenarios, low end, high end. We're committed to somewhere between 45 to 75 centimeters. Now, it's also important to note that with that climate inertia, our oceans aren't just going to stop warming at 2100. They're going to keep warming. So we're going to keep seeing change long after the end of the century. That's that climate inertia. Okay, so our sea level rise, I showed this to you a bit earlier, but again, we've seen close to a foot of global average sea level rise. What's going to happen to our oceans? Well, more carbon emitted to the atmosphere means more carbon absorbed by the oceans and a decrease in ocean pH. Again, the blue line is the low end emissions and the red line is the high end. Keep it in mind that the pH scale is a logarithmic scale. So every change is actually multiplied by a factor of 10. So a huge change, our models, pretty much all of the oceans become more acidic. How is it going to impact our people? Well, this is hard to model, right? We don't know exactly how things will change. We can make general, big picture conclusions, right? The amount of food we can grow will be impacted because we can only grow foods and certain products in different climates, and those regions are changing. We're going to see more damage from floods and storms. We're already seeing that, right? Florida just got hit with another hurricane and very close to the region that was hit last year by Hurricane Ian. Increased health impacts and burdens from malnutrition, infectious diseases like valley fever and West Nile virus, where the distribution of disease vectors can live, increased mortality from heat waves, floods, and droughts. And that puts a burden on our health services, especially in a country that doesn't have equal access to healthcare. How will climate change impact people? Again, water, ecosystems. You can read through it. We know things are going to happen. Okay, it's not a question of whether we understand it anymore. It's what we're going to do. Real life changes, like what if we're talking at the dinner table? What matters to some people is how many days it's going to be hot, right? We're all living through this heat and maybe we don't have air conditioning. I lived in the graduate housing at UCI. There was no air conditioning, okay? It was hot some days. It sucked. Okay, I know at night I was putting like ice packs in my bed to try to cool off. That is the reality of a future with a warming planet. This is showing the projected change in the number of days above 90 degrees. So there's places where more than 60 days a year will be above 90. There are places where huge amounts of people, huge communities don't have access to air conditioning even today, right? And why are we building new dormitories that don't have air conditioning? I don't know. And the number of days below freezing becomes less. So if you're interested in skiing and snow sports, well, it's going to be harder for those places to have snow. So that's going to impact the economy and those people, the people that, rely on that for their well-being and their way of life. Other real life changes that we're seeing in front of our eyes are, these Canadian wildfires this year have been unprecedented. The atmosphere is warming. We're getting more lightning strikes in the Canadian region in the Arctic than ever before with these thunderstorms. That is the one way we get fires that are not via human ignition, impacting air quality. We are going to see on Thursday that air quality is directly linked to mortality. When you breathe in polluted air, you can impact your lifespan. And people, unfortunately, are living in places that have really bad air pollution. So climate change by 2100. And again, our climate's just not going to stop at 2100. It's not going to be like, okay, I'm happy again. It will continue on into the future. And so what we do today matters, even if we don't see the impacts right away. So here's our range of projections, our IPC scenarios. We're currently above 1 degree. We're sitting right around that 1 degree. If we keep going up 2 degrees, our Arctic becomes ice-free, our coral reefs will die, and we can keep going up and up. The question, though, is what are we going to do about it? And so on Thursday, we're going to talk about what we can do. And you all are going to present solutions that are already in place or that could be implemented pretty easily as your final projects. All right, so that's all I have for today. If you have specific questions you'd like addressed about the homeworks, since number 4 is also available now, happy to answer them. Otherwise, please use this time to work on your projects, get ahead on homework, and I'll see you Thursday.